Good. So in this lecture, we're going to give examples on numerical differentiation. So given compute dy dx given x equals to 1.2, x equals to 2.2, and then this is question 1. Question 2, it's not given. Compute dy dx at this point, and then this one at same points. X equals to 1.2, x equals to 2.2. So immediately we see a question of this kind, what should come into your mind is to draw a difference table. I remember I said that difference table, the values you fill in a difference table, numerical values, are the same whether you are referring to it as a forward or a backward. So let's draw the difference table. So when x is 1.0, is y is 2.7183, then 3.3201, 4.0552, 4.9530, 6.0496, 7.3891, 9.0250. So let's now give in the differences. So this one, so this is the first difference, second, third, fourth, fifth, sixth. So when you carry out this difference, please confirm these values. So next is 0.7351, 0.8978, 1.0. Please try to confirm these values. Confirm these values. So this is 0. So this is the difference table. So try to confirm these values. And then the next thing, now we want to find the value of dy dx. So remember when I say, when you're asked to find, when they say dy dx, is the same thing as saying df dx. So dy dx at x equals to 1.2. So let's go to the difference table and then see where there's 1.2. Now this is where we have the 1.2. Just the same way we explained on how to use a difference table, whether you're using Newton forward or Newton backward. When the value is near at the beginning of the table, then use Newton forward. When the value you want to approximate is near the bottom, then use the Newton forward, Newton backward. And when the value is around the middle, then use Stirling formula or Bessel's formula. So then that's remains the same even for numerical differentiation. So we come here and identify the 1.2. So this way you have the 1.2. So then this 1.2 is this value here. It's one of the mesh points. So therefore, you pick this diagonal. That's the diagonal that corresponds to 1.2. So therefore, this like this becomes like it's not, this is f naught, then this is the first forward. So then, because it's near the beginning, then we use the forward formula. 1.2 is near the word formula. And then the other thing was 1.2. So 1.2, not 1.2.2. So 2.2 is at the bottom. So this way I have 2.2. So for 2.2, then we will use this diagonal here. So because 2.2 is at the bottom, then we use the Newton backward. So this, remember, this will be Newton backward, while this one will be Newton forward. Assume we had been asked to find values at 1.6, which are the middle. We've been asked to find at 1.6, which is at the middle, then we'll use either Bessel's or Stirling formula. So please check in the reference textbook on how you need to carry out differentiation using Newton's Bessel's or Stirling formula. The values at the middle of the difference table. So therefore now, this, for the case of 1.2, we are reaching up to the fifth difference. So we need to write our formula up to the fifth difference. So because 1.2 is at the beginning of the table, then we use the Newton forward formula. So which would be given by 1 over h forward f naught minus a half forward squared f naught plus a third forward f naught minus a quarter forward 4, then plus 1 over 5. So we reach 5 because we have up to fifth difference. Up to fifth difference from our table. So this becomes the first, second, third, fourth, fifth. So therefore, replacing in the values we'll have. So therefore, we need to get h is simply given by the distance between two consecutive mesh points, which will obviously use 0.2. And then x naught for this case is 1.2, and then f naught is 3.3201. So therefore, you remember x equals to x naught plus ph. So this is how we get the p to be 0. So x is 1.2 because they want us to find the value at 1.2. So we have 1.2 equals to 1.2 plus p h, which is 0.2 p. So this would be 0 equals to 0.2 p. So this means p equals to 0. So this is just by the way to show why we are saying that we are using p equals to 0 in the formulas we are deriving before. So therefore, dy dx at x equals to 1.2 will be given by 1 over 0.2, which is h, and then the first value is 0.7351 minus a half into 0.1627 plus a third into 0.0361 minus 1 over 4 into 0.0080 plus 1 over 5 into 0.0014. So when you work out, please confirm, you should get 3.325. confirm the working for that. And then for the y dx at x equals to 2.2, because 2.2 is at the bottom, then we use the Newton backward difference formula. And then you see, once you identify that diagonal, it is going up the 6th difference. So then you'll have up to 6 difference. You go up to the 6th difference. So we have so the formula is 1 over h into f naught plus a half plus a third plus a quarter plus a fifth plus a sixth. So h still means to be 0.2. So you have 1 over 0.2 into, so the first value there is given by 9 point. So 1 point. So remember, so this one here. So in this difference here, so we have 0.71. So then 0 point up to then, yeah, that's fine. So therefore now, so 0.1.6 359 plus a half into 0.2964 plus a third into 0.0535 plus a quarter into 0.0094 plus a fifth into 0.0014 plus 1 over 6 into 0.0001. So work out to get the answer to that. And then for the second case, we have d squared y dx squared at x equals to 1.2. So remember the formula is 1 over h squared into second minus third plus 11 over 12 and then minus 5 over 6 . This is the formula. So when you replace, we'll get now d squared y dx squared at x equals to 1.2 is 1 over 0.2 square into, now here you have to be very careful how to identify the values. So the second difference of F naught is 0.1627. So note, you need to use the value in the second column. So 0.1627 minus the third difference is 0.0361 plus 11 over 12 into 0.0080 and then minus 5 over 6 into 0.0014. So when you work out, you get 3.318. So you have to be very careful on how to identify those values to replace into the formula. And then lastly, d squared y, dx squared at x equals to 2.2 is 1 over h squared by definition into squared f naught plus plus 11 over 12 plus 5 over 6 and then plus next term after 5 over 6 should be given by 137 over 180 per 6. So replacing the value, so we have 1 over 0.2 square into so we have 0.2964 plus 0.0535 plus 11 over 12 into 0.0094 plus 5 over 6 into 0.0014 plus 137 over 180 into 0.0001. So work out to get the answer. And that should be 8 point something. So that is how we work out questions on numerical differentiation. So when the values are placed as an exercise, find dy dx at x equals to 1.6 and d squared y dx squared at x equals to 1.16. Get d cubed y dx cubed at x equals to 1.2, dx cubed y dx cubed at x equals to 2.2. Remember, for these first two, you need to use Sterling's or Bessel. So get more examples on the same and then do practice. Thank you.